In this video, we're going to introduce you to the concept of complex numbers. We're going to represent them graphically, and we're going to show you how to operate them with the basic sum, difference, multiplication, and division operations. Let's start by considering the quadratic equation x squared plus 1. Now, we know that if we wanted to solve this equation for x, we need to move the 1 to the right-hand side, and we get x squared is equal to minus 1. And here we will find the first issue, and that is that there is no real number such that when you square it, you get a negative number. Negative numbers, when they are squared, they become positive, and positive, when you square them, they remain positive. So there is no real solution for this equation. So what we can do at this point is define a new number. We are going to define the number I be defined in such a way that I squared is going to be equal to minus 1. And this is the definition that we're going to use for complex numbers. So my number I is what I'm going to call an imaginary number. And I can represent it also through the expression I is equal to minus 1. This imaginary number gives birth to a bigger set of numbers, because now I can multiply this by any other number. For example, I can multiply it by 3 to get the number 3i. I can multiply it by minus a half to get minus a half I. I can multiply it by pi to get pi I. So I am creating a whole new set of numbers that I'm going to call the imaginary numbers. Now, when I combine these numbers with other real numbers using addition or subtraction, for example, let's say you get the number 3i and then you want to add 1, or say you have the pi I and you want to add root 2. What you're creating now is another set of numbers that we are going to call the complex set of numbers. Now, the imaginary numbers, they can all be thought of as you're adding plus 0 to those numbers. So the imaginary numbers are a subset of the complex numbers. We can represent this information in the following set diagram. So in this diagram, we have the natural numbers that we know. The natural numbers, we use them to count, so it's going to be the numbers 1, 2, 3, etc. When we combine those numbers with 0 and the negative numbers, that's when we get the whole set of integers. And when we include all the fractions, we get the rational numbers. So here we can find numbers like 2/3, like 4/9, any number that can be written as a fraction. And when we combine those with numbers that cannot be written as fractions, such as pi, e, or the square root of 2 minus the square root of 3, etc., then we get the real numbers. Now, we have just defined the number I, which introduced a whole new set of imaginary and complex numbers. When we put all the real numbers together with these new numbers, so if we put numbers like 3i or like pi I or like root 2 of I, and also numbers like 3i minus 1 and 6i plus 1/2, then we are getting a whole new set of numbers that is called the complex set of numbers. Generally speaking, a complex number is going to have two parts. One is going to be the real part, which is the part of the number that contains only real numbers, and the imaginary part, which is the value that is always multiplying the number I. So when we put together the number like this, we call it a complex number. We have been using the letter x, y, a, b to represent real numbers. We are going to use the letter z to represent complex numbers most of the time. So we are going to say the real part of z is the number a, and the imaginary part of z is the number b. Graphically, we can represent this number z as a coordinate pair, as we would with a regular xy coordinate. But the difference is that now the horizontal axis is going to represent the real part of the number. So we have a on the horizontal axis, and the vertical axis is going to represent the imaginary component of the number. So that is why b is here. And put together, the point or the number z equals a plus ib would be represented by this point on the two-dimensional space. So how do we operate these numbers? So let's begin with addition. So let's consider two numbers. Z1 is going to be a1 plus ib1, and a second number, z2, that has components a2 plus ib2. Addition of the numbers z1 plus z2 will happen component by component, because a1 plus ib1 plus a2 plus ib2 can be treated as you would a polynomial. And what that means is you can do similar terms. So I know that I can group the terms that have I and the terms that don't have I together. So A1 and A2 don't have I, and B1 and B2, they do have I, so I can put them together, taking I out as common factor, so that the real part of the sum is going to be the sum of the real parts, and the imaginary part of the sum is the sum of the imaginary part. As an example, let's consider the numbers 3i minus 1, and let's say we want to add that to the number 6i plus 2. So what we have to do is add minus 1 plus 2, and that should give us 1, and also 3i plus 6, and that should give us 9i. So the resulting number is going to be 1 plus 9i. Subtraction is similar to addition. So in general, let's consider the same numbers that we had in the previous case. So a1 plus ib1, z2 is a2 plus ib2. And if we want to do the difference of z1 minus z2, we just need to keep in mind that we are going to have to change the sign of z2. So a1 plus ib1 minus a2 plus ib2. And because we said we can treat this as a polynomial, then we can break that parenthesis by distributing the sign, and we get minus a2 minus ib2. And then the only difference with respect to the sum is that the difference of two complex numbers is going to be the real part is the difference of the real parts, and the imaginary part is the difference of the imaginary parts. For example, let's take a difference of two numbers. Let's consider the number 2i plus 1 minus the number minus 3i minus 1. In this case, we can write this as 2i plus 3i plus 1 plus 1, and that is 5i plus 2. Now let's consider the multiplication. Similar to the two cases above, we are going to use these general numbers, z1 and z2, and we are going to multiply them as we would a binomial. So a1 plus ib1 times a2 plus ib2, you will need to do a distribution by multiplying term by term. So we can do that. A1 times A2 plus I a1 times b2, and then we also have to do the product of ib1 with each of the terms in the second number. So that is going to be plus ib1 a2 plus I squared b1 b2. Remember that the definition of I was I squared is equal to minus 1. So we can simplify this expression by writing it like this. A1 A2 minus B1 B2 is the real part plus the imaginary part, which is A1 B2 plus B1 A2. And this is what the product would be. Let's consider the example. 3i minus 1 multiplied by the number 2i plus 1. So we want to do 3i times 2i and 3i times 1. So 3i times 2i plus 3i times 1. And also minus 1 times 2i and minus 1 times 1. Minus 1 times 2i and minus 1 times 1. This is 6i squared plus 1i minus 1. And that is equal to I minus 7. Before we can introduce division, we need to introduce one new operation, and that is the complex conjugate. These complex numbers z of the form a plus ib have a counterpart that is called the complex conjugate. The complex conjugate is going to be a reflection around the horizontal axis of the number z. So, for example, here we have a complex number z equals a plus ib. The complex conjugate of this value z would be a reflection of this number around the x-axis. So instead of having coordinates a, b, it will have coordinates a minus b. And this resulting point is what we call the conjugate, and we represent it with z with an asterisk, or also in some textbooks you can find it like z with a bar on top. We are going to use more frequently the asterisk notation. And what that means for the complex conjugate is that the coordinates a remain, but there's a change in the sign of the imaginary part. So every time they ask you to find the complex conjugate, they are asking you to write the same number, but swapping the sign of the imaginary part. Geometrically speaking, we're talking about a reflection around the horizontal axis. And now that we have the complex conjugate, we can introduce division. Division as such, as a direct operation between two numbers, it doesn't exist. But what you can do is you can use a complex conjugate to find the division of two complex numbers. So let's assume two different numbers, z1 and z2, like we did for the previous operations. So z1 is a1 plus ib1, and z2 is going to be a2 plus ib2. Now, what we want to calculate is going to be z1 divided by z2. Now, what happens in this expression is that we can't really calculate it. We need to substitute this operation with a process that we can actually do, and the complex conjugate will allow me to do it. So, if you look at the definition of the complex conjugate, you are going to be able to see a property. Say for the general number z, and you want to multiply that by its complex conjugate. So according to what we have above, that is going to be z plus ib times a minus ib. And this is a square difference, which means the product of a number and its conjugate is equal to a squared minus I squared b squared. And that is the same as a squared plus b squared. So what we have here is that the product of a number and its complex conjugate counterpart is a real number. The I part has completely disappeared because it's a square difference. So what's the advantage of this? We can use this fact to take the division Z1 over Z2 and multiply it by the complex conjugate of Z2. And in that way, we are going to have a division by a real number, which is possible to do instead of the division of a complex number. So this is going to be Z1 times Z2 complex conjugate divided by Z2 times Z2 complex conjugate. Now, based on what we know, the top is going to be A1 plus IB1 times the complex conjugate of Z2 is A2 minus IB2, and everything divided by the square of the real part of Z2, which is A2 squared, plus the square of the imaginary part, B2 squared. This is going to be how we're going to calculate division, by reducing it to a problem of multiplication. Let's do an example. Let's say you want the number is 3i minus 1 and Z2 is the number I plus 1. And say you want to do Z1 divided Z2. So what we said is, what you want to do is calculate what is the complex conjugate of Z2. That's going to be minus 1i plus 1. Remember, we just switch the sign of the imaginary part. And we're going to multiply top and bottom by that. So we're going to substitute this. This is going to be 3i minus 1 divided by 1 plus I, and I'm multiplying by 1 minus I and 1 minus I. Now the bottom becomes the sum of the squares of the real and imaginary part, so that is simply 1 squared plus 1 squared, and the top is 3i minus 1 times 1 minus I, so that is 3i minus 3i squared minus 1 plus I. Simplifying the top, we get 4i plus 2, and the bottom is 1 squared plus 1 squared, that's 2. So the final answer would be 2i plus 1.